For centuries, we have tried to engineer a machine that can think. But now that the hardware is finally speaking, the experience is disorienting. We look into the machine and something unexpected looks back. In the 1960s, computer scientist Joseph Weizenbaum created a simple chatbot named Eliza. It operated on basic rules, mostly rephrasing user statements as questions. Yet those who spoke to Eliza immediately began attributing real emotion, intention, and a mind to the software. Modern large language models exploit this exact same cognitive vulnerability on a massive scale. By generating highly plausible, coherent text, they tap into our evolutionary instinct to assume a human mind is behind a human-sounding sentence. When we read a convincing paragraph, we instinctively imagine a ghost in the machine. This raises a difficult question. Is the intelligence we perceive real, or are we simply projecting our own biological traits onto a sequence of code? To manage this uncertainty, we often fall back on the defense of dualism. This is the assumption that true cognition and consciousness are exclusive properties of organic matter, the unique result of millions of years of biological evolution. Authoritative voices in linguistics and science, such as Noam Chomsky, argue that modern artificial intelligence is a sophisticated parlor trick. Under this view, these models possess no genuine comprehension and no real creative spark. We label these systems as mere probabilistic text generators to maintain a distance. This terminology serves to protect the status of human intelligence as a distinct, unreplicable phenomenon. Mechanically, that description is accurate. Large language models function by predicting the next most probable token, the small chunks of text that make up our words. The underlying process is entirely mathematical. Text is converted into numbers and mapped into high-dimensional vectors that represent meanings. Consider the values are multiplied through massive grids of parameters to determine which word should follow next. This is a rigid world of multiplication and addition, yet the output it generates is fluid, technically proficient, and appears to reflect an understanding of context. The mechanism relies on statistics, but a purely reductive definition fails to account for the novel behaviors that appear when these models reach a sufficient scale. Consider the threshold known as grokking. This is the point where a model moves past simple memorization of its data and begins to operate according to the abstract rules of the system it is studying. Researchers observed this while training a small neural network to perform modular arithmetic. Initially, the model failed. It could only recall the specific math problems it had been shown during training, failing whenever it was tested on something new. In this chart, the error rate for unfamiliar problems stays high and flat for thousands of steps. The model appears to have hit a ceiling, but suddenly, without any change to the data, the error rate for those new problems plunged toward zero. The model had autonomously generalized the math. By examining the network's internal layers, researchers found that the model had developed hidden representations of sine and cosine waves. It was using these cyclical patterns to calculate the modular arithmetic. These trigonometric waves were never programmed into the system. The model was only given raw math problems and answers. It discovered these mathematical structures on its own as the most efficient way to solve the puzzle. The network had transitioned from a memorizer to a reasoner. It built an internal, abstract model of the world to solve problems it had never encountered before. The phenomenon of grokking suggests that comprehension can organically emerge from probabilistic training. It indicates the just statistics argument may be missing the most important part of the story. Understanding this requires a shift toward gradualist functionalism. This perspective defines a system by what it does, rather than the physical materials it is made of. We accept a mechanical pump made of titanium and plastic as an artificial heart. We call it a heart because it performs the function of circulating blood throughout the body. We can apply this same logic to cognition. When an artificial system demonstrates the capacity for inference, adaptation, and reasoning, we must ask why we refuse to call it intelligent. Our hesitation is often less about a scientific boundary and more about a moving goalpost. We redefine intelligence as whatever machines can't do yet to maintain our sense of human uniqueness. This defense becomes harder to maintain when we look at the human brain. Cognitive neuroscience suggests our biological mind operates as a stochastic predictive engine. Your brain is constantly calculating probabilities based on past experience. guessing the next sensory input or the next word in a sentence before it even arrives. There is an irony in dismissing machines for relying on statistical prediction. Our own biological neurology uses a highly similar predictive architecture to navigate the world. If human thought emerges from a physical system processing probabilities, the line between a simulated intelligence and a biological one starts to disappear. Both are systems derived from the same mathematical principles. The real source of our dread is the realization that human cognition is just another physical algorithm. These machines aren't just imitating us, they are exposing the algorithmic nature of our own intelligence.